What is WebAssembly? You might be familiar broadly with this technology, but not of why it's so interesting. This is part one of a multi-part series. WebAssembly is a technology that powers a lot of modern tools. On screen, we have Squoosh, Ruffle, Godot, Zellige, Fermyon, and Figma. These tools use WebAssembly, either for major features or critical parts of their technology. It's also widely being adopted in places that might be surprising, like Google Sheets. So what is it? WebAssembly is fundamentally a language. It's a language that is also a compile target, so you can compile your programs written in C, Rust, Go, and Zig to WebAssembly. This WebAssembly is then run by an engine of sorts. If you're familiar with how the JVM bytecode works, it's kind of like that. We're compiling to a bytecode format which looks like assembly. It was developed as a web standard, thus the name WebAssembly. Whereas our machine code is written for a specific kind of hardware, Wasm bytecode is more generalized. For those familiar with the JVM, you'll see lots of parallels here. This makes answering the question, how fast is WebAssembly, not straightforward. It's a language that is run by a different engine depending on the context. It's like asking how fast algebra is. On screen, you can see some of the most popular engines. V8, which powers Chrome and Node, SpiderMonkey, WasmTime, Wasmer, and Wasm Edge. The stronger comparison might be JavaScript. It usually runs pretty quickly, but that's because you're seeing it run in engines like V8, JavaScript Core, and SpiderMonkey, whereas the QuickJS engine might be much slower for CPU-bound tasks. The speed of WebAssembly depends on the engine and context. In practice, WebAssembly typically runs at 85 to 95% of native speeds for compute-heavy tasks. But you can also compile Wasm itself to native code. Wasm 2C, W2C2, and Wastrel will let you get native performance with the trade-off being a security downgrade. But really, the goal of Wasm is to be fast enough, to make the performance trade-off worth it for what you're getting out of it. Let's talk a bit more about security. The text format for Wasm looks a lot more high-level than your traditional assembly format. We rely heavily on imports and exports, which is not something you'll see in many others. You see, unlike ARM or x86, WebAssembly has no concept of the OS and very little relationship with the execution context. This also differentiates it from JVM bytecode, which makes some assumptions about its execution context in terms of things like file system access. WebAssembly's security model is deny by default. A module can do nothing unless the host explicitly provides the capability. This makes Wasm a really safe format if you want an embeddable language. Platforms will often use JavaScript or Lua as their scripting language, which is fine but locks you into one of two languages. Instead, they can support Wasm and just let you choose for yourself. This security model also allows you to sandbox untrusted user programs. For Figma, this means running JavaScript plugins in your browser by compiling QuickJS itself to WebAssembly. For Cloudflare, it means running different Python programs in the same process by running them in a version of CPython compiled to WebAssembly. This unlocks considerable performance gains. Companies like Fermyon are doing this for similar reasons. Security can itself enable performance. Wasm being a general target has the same advantages you get with Java. You don't need to recompile the program, just the engine running it. The same distributable binary can be run in the browser, in your terminal, or on your phone. It's this aspect that seems to have been the most useful, bridging the language gap. A lot of image codecs are now available in the browser by reusing a C program that already existed. There might be a language or ecosystem better equipped to produce a specific set of tools. The same Wasm file works from JavaScript, Python, Ruby, or any language with an embeddable Wasm runtime. Wasm is still undergoing constant development, with new features being introduced each year and new extensions being incubated. Recent features shipped to your browser include garbage collection, atomics, SIMD, and exception handling. Outside the browser, we're also working on better tooling, such as the component model, which lets you define language-agnostic interfaces with WIT, shown here. The W3C working group handles standards, and the Bytecode Alliance tends to iterate on tooling. With all that, development of WebAssembly is mostly opaque to the average developer. This is because you're not actively involved in its development. It's not replacing JavaScript anytime soon. Instead, it's quietly embedded in the libraries and applications you already use. It's likely you personally don't have a use for understanding WebAssembly internals, which is why the educational material is mostly around tooling and not the language itself. But I still think there's a lot of value in actually understanding it. If you like this, you might like understanding WebAssembly a bit more in depth, which we'll be covering in future videos. I'm going to attach some links in the description if you'd like to get ahead of things with more text-based resources. Until next time, thanks for watching.